We're going to hold off on that till tomorrow. We still want to go back to intermediate value theorem, so page 13. We didn't quite finish the problem all the way, so let me recap and then finish the problems, and then we'll do some more practice today. I mean, if there's time, yeah, that'd be great if we can jump into 1.5. So page 13. So example 1, we talked about how the target Y value that we're looking for requires a couple of information before we can commit to guaranteeing that Y value. First, we have to make sure that our function is continuous on the closed interval. And with a polynomial, it's always continuous, so you don't have to make any checks. You can just have to state out where you're looking for continuity. We just care about the interval from 0 to 1. And then the second thing is we need to make sure that our endpoints are at a certain location. Okay, we need one endpoint to be below our target Y value, and we need the other endpoint to be above our target Y value. Okay, so make sure that you're comparing your Y values with Y values, and that you're not trying to compare X values with Y values. Okay, that's not going to help us make the appropriate reasoning. So now we know that this guarantee is going to occur. It's just how do we phrase it in a way that that will be acceptable. There's more than one way to do this, but this is the way that can be the most efficient, get all your information across in the least amount of writing. So we can say by IVT, since, thank you, f of 0 is one endpoint, and that's producing a -1, and -1 is less than 0, which is our target, and 0 happens to also sit between the other endpoint, 2, and 2 is coming from f of 1. I know this is a strange notation here, but this is acceptable on College Board. This basically shows all the information that you want to give. You're showing that you're comparing with the correct Y values, and you're showing that the Y values that you're comparing are coming from the endpoints. Yeah.
Well, can you put like f of 1 equals 2 instead of 2 equals f of 1? Like.
Oh, yes, you can. Yeah, you can. I just it just feels a little bit easier to see that connection, seeing the -1 and 0 and 2 together. But yeah, you can flip these around and it'd be okay. And because of this, we know that f of c is equal to 0 somewhere on the interval from 0 to 1. Okay, so this is justification that shows our understanding of intermediate value theorem, and technically this is also part of it, but we've already established this, so we just have to have this somewhere. Yeah.
So if this wasn't a polynomial, how would the know this continuous?
Right. So if it wasn't a polynomial, then we would seek out the denominator and see if the denominator will produce a whole or asymptotes that disrupts the interval. And we're going to see that with the next example I'm going to show you.
So is all we're adding like how to answer it?
I'm sorry?
Is all we're adding like how to answer it correctly?
Yeah. There's one more thing that we haven't done yet, and that is looking for, if I ask you where the location of this guarantee is, that's finding the order pair. So the next problem will find that C value. That's basically the full order pair of the location. But right now we just know it's between 0 and 1, but we don't know where it lands yet. Yeah, so there's one more thing we need to do, but we'll do that in the next example. And we'll do a couple more so we can get really comfortable with it. Okay, next page. So we started this problem, but I will kind of recap what we got so far. Okay. Verify that IVT applies to our rational function on the interval from 5/2 to 4 for f of c equals 6. So this is our goal. We're trying to guarantee a y value of 6, but we're trying to do it without looking at the graph. We're just trying to use IVT. We're just trying to use the most minimal amount of information to guarantee this y value of 6. First off, make sure that we understand this 5 to 4 are x values, that we're never going to compare these numbers with this number, because that's a mismatch in terms of information. The next thing is continuity. Okay, and going back to that question is how do we find continuity issues if it's not a polynomial? So this is not a polynomial because we see variables in the denominator, but this is where we look for discontinuities. We look for discontinuities from the denominator of our rational function. So if I set that x minus 1 equal to 0, I see there is an issue. There is a vertical asymptote at x equals 1. This is the only break in the entire graph. So is this asymptote going to impact my interval? It doesn't. So this is safe. So I know that my function is continuous on the closed interval, and I can go ahead and write that down. Okay. So now the next goal is, can we find out information that will support our goal from our endpoints? So we take our endpoints, we put them into the original function. I saved some time here just to kind of give you what these decimals are rather than having you put it in the calculator. And also on the test, it'll be easier for you to find where you don't have to do a whole lot of number crunching to get there. Thank you. Okay, so let's say one endpoint gives you the y value of 5.8, and the other endpoint gives you a y value of 6.7. Are these numbers going to support our goal of reaching 6?
Yeah.
Yes, right. So we start at a y value of 5.8. You're going to hit 6 somewhere along the way because it's continuous, and we're going to hit 6.7, right? At least once, right? Maybe more than once, but at least once, and that's all we're trying to guarantee. Can we hit that y value of 6 at least once on that interval?
You don't know when it's going to hit.
Not yet, but we are going to look for that location. Okay. But first, let's establish that we can guarantee that that y value of 6 exists. So we're going to write our justification the same way as the previous problem. We'll say by IVT, since f of 5/2 produces 5.8, and 5.8 is less than 6, and 6 is sitting between 5.8 and 6.7, and 6.7 is coming from f of 4. We know that somewhere on this interval, f of c must be equal to 6. On this x value interval from 5/2 to 4. Any questions here? Okay, so I just want to kind of show you don't have to know what the graph looks like per se, but I think it's good to just kind of have some visual to connect with. So this is what our graph kind of looks like. This is our y value of 6, and we were testing between 5.8 and 6.7, and so that's why we know that somewhere along the way is going to hit that y value of 6. But now our next goal is to figure out what is this physical location that it hits 6, right? We want to find out what is the y value, or sorry, what is the x value, or in this case, they call it the c value. What is the ordered pair where this occurs?
Does it hit 6 twice though? Like,
yeah, it looks like it may hit 6 twice, but let's talk about how we can get there algebraically, because we're gonna have to do this without the use of a graph. But I do want to kind of connect with the graph so you can kind of have a visual. How can I go about finding this ordered pair if I know that the y value of 6?
I'll plug it into the function.
Good, plug into the function. Now, where do I plug? How would you use this function to help you find where you're looking for?
So you see 6 equals 2.
Good. 6 equals, well, 6 equals this expression, right? So we know f of x represents the y value. So we insert 6 in for the y, and then we just algebraically solve for x. If we solve for x, we should be able to figure out the location of that c value, because c is our x. Okay, good. So let's try that. So we'll do 6 equals x squared plus x over x minus 1. Okay, so algebraically, maybe it's easier if I just wrote it as a fraction. That way I can just cross multiply and I can just get it all to be everything in the numerator without denominator showing. Right, so the cross product here. So 6 times x minus 1, I want to make sure I either protect it with a set of parentheses or I can distribute through, but I just want to make sure that I don't just say 6x minus 1, right? It's 6 parentheses x minus 1. Okay.
Why wouldn't you factor out the x? Like,
Well, we're trying to solve for x, so we want to try to get everything together without the parentheses, because parentheses kind of gets in the way right now, because we haven't gotten the 0 to show up yet. Now, once we get 0 to show up on one side of the equation, we can begin to factor. But right now, it's a little messy. We want to kind of clean things up a bit. Get some common factors to be together. So it looks like the x and 6x can come together. Now, whenever you see a degree 2, a degree 1, and a constant, we have to go through factoring. We have to bring everything over to one side and get a 0 to show up on the other side of the equation. Okay, so we can factor. So I'll get x squared, subtract the 6x. So 1x minus 6x is what?
-5.
Add 6 to both sides, so plus 6 equals 0. So now we can look for our solution, right? We got everything cleaned up. This is a trinomial factoring problem. Now we can look for two numbers that multiplies to be 6 and adds up to be
-6 + 1.
right, so two numbers that multiplies to be 6 adds up to be -5, -2, and -3. Okay, so let's double check that, right? So -2 times -3 is 6. That's good. -2x minus 3x, -5x.
Does 2 work here? This is -6 + 1.
Well, the thing is, we got to have two numbers that multiplies to be a positive 6. So 6 times a -1 will give us a -6. So that pair doesn't quite work. Right? Because I have to be able to FOIL out and get that. Now, that would work if it was x squared minus 5x minus 6, then 6 and -1 would be good. But this is a positive 6, so I need two numbers that multiplies to be a positive 6. Okay, so what x values do we see here? X equals 2. So, like Connor said, we have two locations where the graph hits a y value of 6. So c equals 2 and c equals 3. Now, are these the answers that would be acceptable for our problem? What do you guys think?
No.
Okay, why not?
Is it the separation's bigger than just like 1 unit? Oh, from the graph you drew.
Okay, we only care about the interval, right? So there may be locations that are true outside the interval, but if it's not part of our problem, then we're not going to give it as a solution. So if we're going just from 2.4 to 2.5 to 4, 2 is outside the interval. So if you look at the graph here, obviously, yes, there is a y value of 6, but if we're only concerned about the interval, then we're not going to make that guarantee. We're only going to make a guarantee of what's inside the interval. So our c value of 2 is outside the interval, and the c value that we want to keep is 6. So basically, the order pair that we care about is 3, 6. 2, 6 is not part of our problem. So we only care about the interval from 2.5 to 4. So 2.5 starts here and 4 ends there. So only 3 lands between, and then the other y value, yeah, it's not part of our interval. Okay, any questions here? Now, I do want to point out a few things about this theorem that is nice, in that you're going to see these repeated things show up across the other 3 or 4 theorems we're going to be seeing over the course of this semester. The first is being able to check for continuity and being able to make a statement about continuity. So that you're going to see repeated regardless of theorem. And then the last thing, looking at your solution and comparing it with your interval and deciding which one falls inside and outside the interval to make your final justification. So these pieces are going to be the same process, even if the theorem that we're looking for will be different across different theorems. But looking for continuity and then checking for the appropriate values is going to be used throughout all different theorems that we're going to see. Yeah.
Are the first two things you highlighted, are those both for looking for continuity? Okay.
I'm sorry.
Are the first two things you highlighted, are those both for looking for continuity?
Yeah, that's right. Looking for continuity, looking for breaks in the graph and seeing if the break in the graph is going to impact the interval. Because if it doesn't impact the interval, then we're safe. But if it does impact the interval, we say the function is not continuous on the closed interval, and then we stop the problem. Okay, we can't do the rest of the theorem if we can't get past that first condition of continuity. So, so even though this, we're introducing this as our first major theorem, we're also learning about the other theorems just by looking at the first and last. And these steps are going to come up again and again, regardless of the theorem. Okay. Okay, let's do a few more just so that you guys can get comfortable with the notations and what you're looking for. So if we can,
There's gonna be another theorem for this one.
I'm sorry.
There's gonna be another theorem.
There's gonna be another theorem, but not for this unit.
Oh, okay.
Yeah, well, sorry, we still have squeeze theorem, but we kind of did squeeze theorem already. So that's going to show up in your homework. But on this test, this is the major theorem that we're going to have to know. Okay. If you guys, I put some review problems a little bit later in the packet, so it's a little bit out of order. So we got to turn to page 20. So we're going to go through the same steps, okay? I'll do one with you and then have you guys try the second and third one on your own, okay? All right, so let me walk through this one with you. So here's our function, x squared plus x minus 1. We know that this is our target, our goal. We want to hit a y value of 11, but again, remember, these are your endpoints, but these are your x values. We don't want to say 11 doesn't land between 0 and 5, so therefore IVT fails. We're not comparing the same things if we do that. Okay, so our condition here is continuity. We have to make sure that we make a statement about continuity. On the test, I'm looking for that statement about continuity as well. So is this guaranteed to be continuous? Yes, you got a polynomial. There's no variable in the denominator. We're safe. You don't have to make any checks. This is going to be an automatic thing. So f of x is continuous, but I do want you to specify, even though it's continuous everywhere, it's only the interval that we care about. So we want to specify that we are only concerned about continuity on the closed interval. Okay, next up, we know the endpoints is going to help us determine if our goal can be guaranteed with just this very limited information. Yeah. That's the y value. Yeah. That's sorry. Y equals 11. So it's basically saying if I look at my graph here, is my graph going to cross the y value of 11? So that's my goal.
We don't have a vertical asymptote.
There's no asymptote here because there's no variable in the denominator. Right. If it was like x squared plus 1 divided by x plus 2, then that x plus 2 would give us a location of a hole or an asymptote. But if you don't see a denominator in the variable, you can always just make this statement without having to think twice about checking for anything. Okay, so let's test our endpoints, right? What do we want out of these two endpoints? We want a y value where?
11.
What y values do we want out of our endpoints?
Oh, you want in between 11.
Right, on one above and one below, right? We want 11 to be between our two endpoints. Okay, so what's f of 0? -1, so we have a number below, that's good. Okay, so now let's plug in 5. 29, that's above, so we know we're safe, right? If we're going from -1 to 29 with no breaks in between, we know we're going to hit 11 somewhere along the way. Maybe more than once, but at least once. Okay, so then let's make our statement by IVT. Since f of 0 is -1, and -1 is less than 11, and 11 sits between -1 and 29, and 29 is coming from my other endpoint. I know that f of c is going to be equal to 11 somewhere on the interval from 0 to 5. Okay, questions? Okay, so now let's find the value C guaranteed by the theorem. So now that we know that we're going to be able to guarantee that value, let's find the order pair. So how do we go about finding the location there?
Sketch out the graph.
Well, we're going to do it algebraically though. Yeah, good. 11 equals. So we know what our y value is. We're going to look for the x. So we just go back to the original equation and you just solve for x. Okay, bring everything over to one side. Don't set x squared plus x equal to 12. Okay, that's not going to be good for us. We want the 11 on the same side as all the equations. We want that 0 to show up before you do any sort of factoring. Well, yeah.
Plus 4 minus 3.
X equals. And x equals 3.
But -4 doesn't work.
Good. -4 doesn't work. You always have to go back and test with your interval, right? Your interval is the extent of your problem. Anything that's outside the interval is not part of your problem. And the more that we get comfortable with this, the better it is, because we're going to see this play out across all different theorems, having to go through that check. It's possible. Yeah, it's possible there's more than one C, but typically if I see more than one, that kind of gives me a red flag, because I'm like, wait, usually there's only one. So I definitely want to make sure and check. Okay. Now, if you only get one, then that's usually pretty safe, because if we can guarantee that there's a location, then if we get one solution, then that one solution is our guarantee, right? But anytime I see more than one, I'm always a little bit, cautious about, wait, maybe that second one is outside. So I do want to test both and make sure that I'm always comparing with my interval. Yeah. Good. So let's say, well, one way that doesn't work, let's say there's a vertical asymptote and that asymptote impacted the interval, then you would say the function is not continuous and IVT doesn't apply. But then let's say these two endpoints do not land on both sides of our target, then we say that IVT doesn't apply, since 11 doesn't land between, let's say, -1 and -5. Right, so basically you just have to make a statement about IVT doesn't apply because I can't get that target to be between my two endpoints. But once you get past this step, you're guaranteed to get at least one solution. So at the end, if you're not getting any solution inside the interval, then something didn't go quite right. So either it's possible that that we made a mistake here, or we know something didn't quite line up.
So it's 2 parts, but there's 2 different answers first.
Yeah, that's right. One answer is to prove that there is a solution, and the second is actually finding that location.
So you usually don't have to sketch out the graph. Like
Yeah. So I'm not expecting you to sketch out your graph. There, you won't have a calculator. So the whole purpose of IVT is that we're making this guarantee without looking at the graph. I mean, if you could look at the graph, then it's easy, just point at that location. But we're forcing ourselves to.
Are most of them gonna be like quadratic? Because they all like.
Yeah.
Is there any like?
Yeah, 97 is a little messy. So that factoring is a little bit harder. So let's just do 96. Okay. So have you guys tried 96? See if you can walk through those steps. But If I give you a problem, it'll be quadratic. I won't give you a quadratic or a rational. I won't give you a cubic. It'll be a little hard for our factoring steps.
What do you like just factor out X? That's probably harder than that.
For what, 97?
For the cubic one.
Well, we can't factor an X unless every term has an X. So 97 doesn't have that, so we can't quite do that. Yeah, it doesn't factor nicely. So we'll skip 97.
You know, it's continuous. You just like assume it is.
Well, this is a polynomial.
Okay.
So you don't see any denominator in the variables, right? It's not like this one where there's a red flag and you realize that yeah, it's not like this one, right? Where there's a variable in the denominator and you realize, okay, if you see a variable in the denominator, you know you have to check for a whole or an asymptote. But if you don't see any variable in the denominator, it's safe. You know it's going to be continuous.
Okay.
Yeah. Okay, how's it look so far? What conclusion can we make?
C equals 2.
C equals 2, yeah.
Why would this like work? Because like this -1 outside of. Confused.
Well, these are X values.
Okay.
And these are Y values. We're comparing these Y values with that Y value.
Oh, okay. So it falls in between. Like,
Yeah, falls in
okay.
between. Any questions? Are we comfortable with the steps for intermediate value theorem? Let's see. Okay, let's get a head start into this 1.5 limits approaching infinity.
Not gonna down these 97.
Yeah, we won't, yeah, we'll skip 97. That's a tough one in terms of algebraic. So let's turn back to page 15. Okay, so infinite limits. A limit is where a function increases or decreases without bound towards infinity as x approaches c. So we've seen different variations of vertical asymptotes, right? We know how a graph can look, right? The arrows can be both pointing in the same direction. Gets closer towards asymptote, they can be both pointing down. They can both be pointing in opposite directions. So we do have 4 options, right, in terms of how those arrows can look, right? So I want to just kind of bring that to your attention and have that in your head. Right. So we have 4 different ways that the arrows can move towards the asymptote, right? And if we're looking at a rational function, that just means a variable in the denominator here. And if I can show that factors in the denominator don't cancel, then we know it's a vertical asymptote. We know it's not a whole, right? A whole would have common factors that match and pair up and reduce. But any leftover factors in the denominator, we know is where a vertical asymptote exists. So example 1 says find all the vertical asymptotes of our function. Let's just go ahead and factor everything and we can find those factors, right? So trinomial factoring here multiplies to be 2, adds up to be -3. Yeah, -2, -1. Difference of squares below.
+2 minus.
So we have 2 factors in the denominator. But are both of these, are they different from each other?
You cancel out the x.
So we know that this is a whole, right? We know that's not a vertical asymptote. Vertical asymptote is going to be at -2.
That's it.
Yeah, so I just want to make sure that we, just as a quick review, right, how we can identify a vertical asymptote. Basically, any factor in the denominator, variable in the denominator that don't cancel out is where you find your vertical asymptote. Okay, so we're good with that. Okay, now let me show you. I'm going to skip all these explanations here. Just going to show you what we can do, and we've seen this before. But I want to extend a bit more past what we did. Okay, so I want to do 3 examples here. I'll call this example 1, and that's exactly what the one that you see here. We're going to do the limit as x approaches 2 of x plus 1 over x minus 2. Okay, let's go through our steps. Okay, we'll go through our steps like we normally would in the past. What's our first step? Always
0.
right? Plug in
Plug in 2.
right? Plug in 2. And what do we get? 3 over 0. What does that tell us? That's the vertical asymptote. And what would you conclude? That the limit what?
It doesn't exist.
Good. Limit doesn't exist. Okay. And then we would stop there, right? That is as far as we went from previous problems. Okay. So are we good with that? So now, well, we know the limit doesn't exist. We know, well, there's only one asymptote, right? But the graph can still behave in different ways, right? So what we're going to discover today is how are the graphs behaving even though the limit doesn't exist? Okay, so we're kind of delving into under the category of does not exist. How are the graphs behaving? And that's what our next step is, trying to figure out how things look. So, but we know that the limit doesn't exist, right? We know what it looks like for a limit not existing. So let me show you a one-sided limit and how you would approach this process. Okay, so let's say we do limit as x approaches 2 from the right side of 2 of x plus 1 over x minus 2. So forget the fact that we did number 1. Imagine this is a fresh problem that you've never seen before. What would your first step be?
Plug in 2.
Plug in 2, right? So just 2. I want you guys to continue. So once I introduce this something new here, our go-to is to forget about this first step. So I don't want us to forget this first step. We always want to plug in that whole number that we see in front of us. Okay, so keep that in mind. Okay,
You don't worry about like the sign that's behind it.
not yet, not yet. Okay, so we're gonna plug in just the 2, and again, we get what? 3 over 0. Again, we know there's a vertical asymptote. Again, we know that the full limit doesn't exist, right? But is this asking for the full limit? No, it's only asking for the behavior of the graph as it approaches that vertical asymptote. So what are the only options that the graph could do as it approaches the asymptote from the right side? Either what?
Go up or down.
Positive infinity or
Negative.
infinity. So you know there's only 2 options here, right? Because you know there's vertical asymptote and you're asking just for the movement from the right side. So there's only 2 options, right? It's either positive infinity or it's negative infinity. Those are the only 2 options. Okay, so are we good with that point so far? Okay, so it's a 50-50 shot, but we're gonna have to do something to find between our 2 options. Okay, so the way that we're gonna do this algebraically or numerically without the use of a graph, obviously if we can see the graph and we can just tell how the graph is moving, is we're gonna pick a point really close to 2, close enough where it will give us an indication as to where the graph is moving. Now, what's the number to the right of 2? 3. Okay, we're going to pick a number even closer than that. Okay, so typically the safe number is a decimal number that's within 1/10 of 2.1. So we're going to test 2.1. And you may feel like this is difficult to do without a calculator, but we're just going to enter 2.1 in for x, but we don't care about the decimal value. You're just going to tell me if the numerator is positive and the positive or negative, and the denominator is positive or negative. So I'm going to plug 2.1 in for x. 2.1 plus 1 is
3.1.
Say, tell me if it's positive or negative. Positive, okay, so we just care if it's positive. 2.1 minus 2, also positive. Okay, positive over positive is still positive, so that tells us that with a pretty good degree of certainty, we know our graph is headed towards positive infinity.
So what are you doing? Sorry.
So we're testing what we're choosing between these 2 options. And if we pick a number close enough to 2 from the correct sign, we can have an idea how the graph is moving.
So you plug it in back to the.
Yes, right, back into the original. So 2.1 plus 2 is positive. 2.1 minus 2 is positive. So positive over positive is positive.
You don't care about like the numbers, it's just signs.
Just the signs, yeah. The signs will tell me which direction it's going. That's all I care about.
If like either one was negative, it'd be negative.
Say it again.
What if it's like a positive and then a negative?
Yeah, if it's positive over negative, then it'll be negative infinity. If it's negative over positive, it's also negative infinity. What if it's negative over a negative?
Positive.
Positive infinity, yeah. Okay, let's do one more instance here. This is coming from the other side here. Okay, we're going to ignore the fact that we see the minus here. We're just going to go through our steps here. So if I plug 2 in, again, I get 3 over 0, vertical asymptote. Normally, you would say limit doesn't exist, but you realize, oh, it's only asking from the left side. So I know it's one of these 2 options. Right? It's either going up to positive infinity or it's going down to negative infinity. So now, what number can I test to help me decide between those 2? 1.9. Okay, so into the x's it goes. 1.9 plus 1, is that positive or negative? 1.9 minus 2 is negative. So positive over negative is negative. So therefore negative infinity. Are we okay so far? So this is where the danger comes. The danger comes is that now that you know that there's decimals involved, the tendency is that we want to do decimals a little too early. Okay, whenever we see that one side limit, you're going to want to think that you got to do decimals. But you only do decimals if you realize it's a vertical asymptote. If it's anything else, if it's 0 over 10 or 0 over 0, you're going to pretend like as if that one side limit doesn't matter, because it's not going to play a role for you unless it is a vertical asymptote. Yeah.
So is there any case where you're gonna have to have us draw the graph out after solving?
No. I just want to kind of show you that, because it's a vertical asymptote, you only have a couple of options in front of you, and then you only are doing decimals if you're deciding between the arrows at a vertical asymptote.
It's usually between like a tenth and tenth of the number.
That's right. Yeah. So you always want to pick a between the 10th and the 10th. Let me see. I have a few more minutes here. Just one. Okay. I want to talk about the issue that students have tomorrow, but just real quick here. Let's say I approach -2 from the left side of 2, x plus 3 over x plus 2. Now, if I'm choosing a number to the left of -2, you got to think of, just be careful here. If you're on the negative side of things, to the left of -2 means I got to pick a number on this side, right? So what's the number to the left of -2? Yeah, so this one will be test x equals -2.1. So just be careful. Everything's going to be opposite if you're on the negative side. And obviously, if you're doing limit as x approaches -2 from the right side of -2, then that means I got to pick a number on this side. And the number on this side will be what? -1.9. Yeah, so just be careful. When you're on the negative side, things are going to be opposite, right? Just because of the way number line works. Okay, so this is a preview to tomorrow. So we'll do a lot more practice with this tomorrow, and I'll talk about the danger that students run into. But you guys have homework tonight, just finishing up from 1.3 and IVT and squeeze theorem. So check your homework, check your calendar. Okay, come get your phones.
Thanks.
Yeah, thanks.
Is there any more new topics we're learning for the things?
Yeah, horizontal asymptotes, but this is the most difficult one. After this, horizontal asymptotes is a little bit easier. But another hard thing is just seeing everything mixed up and trying to decipher which one you're doing.
Oh, you're not gonna be given that.
Right. So you're gonna have to figure out which category you're in. Yeah, we'll have Monday and Tuesday for test review. And I'll give you a test review packet too.
That's what you
Good, thank you.
Bottom.
Yeah.
1 through 5.
Yeah.
Oh, I'm just confused. I started getting. What would, but I don't understand what it's asking. It's like giving me a number to compare the interval.
A 0. So 0 just means.
Okay, this one it's. I don't.
The 0, yeah. You're just checking to see this.
I'm someone to stick around my back.
Yeah, don't worry about that. Yeah.
Just everything about zero.
Mhm.
Okay. Just worded weird.
Yeah.
I just like, you should pack them. Forget.
Sorry, it's kind of.
You like starting.
It's cute. Let's do it. Because I'm trying to find.
Yeah, that's more of a calculus question, but I don't think I was.
Obviously, you don't. I'd say sit down and close that away.
That's from
Whatever it takes.
Goal, pretty good.
Did I sign that?
Yeah, to me too.
It's
Oh, yeah, 65. Just get to the point of guaranteeing it and then don't worry about that last thing, because that won't give you one with a cube.
For calculus, like, is it like one of those classes where like everything like builds on each other? You know, like so you can like remember what you did.
Yes. Yeah.
Yeah. Okay. So like we're gonna do limits like additional units to the graphs.
Okay, so the interesting thing about limits is that after this, we're not gonna see too much of it.
Okay.
There's one future unit that's gonna make limits a little bit easier. But starting with chapter 2 with derivatives, then everything kind of builds on top of this. So limits, it's a little bit of a standalone. We're gonna see a connection between that and derivatives, but then once we see that connection, we're gonna let it drop off and we can just do.
Okay.
Yeah, starting with unit 2, that's the true foundation. It's really like a precursor. It's on the EP exam, so that's what we also have done.
Right.
Yeah.
So unit 2 is like you're doing derivatives like most of the year.
Yeah, derivatives is gonna last. It's gonna be mainly first semester, but we also need it for second semester, so.
When friends told me to take this class, they said second semester gets a lot more complicated. Like
It does, yeah, because we need derivatives and antiderivatives. But if you build a good foundation for first semester, second semester will just feel like a natural progression. It won't feel like a big jump.
when are we starting getting calculators? Like
Sometime after,
after that?
yeah, I would say sometime when we hit unit 3, we're gonna see more of it. But still, we're gonna try to do a lot of things without a calculator. But eventually we are going to have to get comfortable with it.
So unit 2, we won't need it. It's much cheaper.
Sorry?
Unit 2, we won't need it.
Unit 2, you won't need it.
Okay.
Unit 3, we will.
This unit we don't need it.
Yeah, this unit won't. need it.
You know, always say econ every like, can you give us like notes to do? Yeah. Oh. I was never follow them. Okay. I'm not putting.
Appreciate it.
I was able to do
Happening stuff? Yeah, I know, learning how to use the calculator, the SAT would be so much better, because I can like graph functions. I have no clue how to use.
Well, you know that.
Because- Yeah. Maybe I should look at that.
All right, Steve, have a good day. Hey.
How are you?
Good.
Yeah. Like I would do, like if they took the keys and those songs, I put it in a key motor. I'd do it. I mean, if everyone is saying looks like maybe.
It puts your test there. You lose your back.
That's like. When you want to start, it's like, I like the board. So it's the truck call. Oh, the truck went on here. Yeah, that's what it's. He's like, good. Two, you went following me right now, you got 46. Yeah. Lots. That fucking ass. Yeah.
I didn't think. You have that, you have that in your bank. And this, I don't think I'm hoping you got about 5%, but. Like, what is my, what is, you know, I think it's safe thing. Because like, by the way, so you guys don't have a spoken response to share. Thanks to you, the two people who for you to the most. It's the wrong. I know. No, I was like, I give you a I said like, I was the other thing. I like more stuff. I'm not gonna take it. But 50%. Oh, I went from co-founder to like, and her, you're one to like 12%. No, you lie. Like, he was like, really, once he came back, he was like, money, it's like 10%.
Like, you know, like.
Yeah, it's like.
Oh, no,
That's way. That's not a water. It's like. Yeah, like, I don't know.
Just like some fucking first. I'm going to.